If you followed a compass north in 1900, you wouldn't end up in the same place today. In fact, you'd miss it by hundreds of kilometers. Earth's magnetic field, the invisible force that protects us from solar radiation, guides aircraft, satellites, animals, and even your smartphone, is changing. And not slowly. One of its most important reference points, the North Magnetic Pole, is moving faster than at any time in recorded history. But why is it moving? Is this driven by deep forces in Earth's core, or is climate change playing a role? What happens to navigation systems when north won't sit still? And what about animals that migrate using magnetic fields? And then there's this, a growing weak spot in Earth's magnetic shield over the South Atlantic, a region that satellites actively try to avoid. We have to go from molten iron 3,000 kilometers beneath your feet to satellites orbiting above your head to understand what is truly happening to Earth's magnetic field. Earth doesn't have a magnetic field because it's a giant bar magnet. It has one because the planet is running a 4 billion-year-old electrical generator. Let's briefly explain what's going on. The Earth has a solid inner core, with a liquid outer core of molten iron and nickel. As molten iron rises, cools, sinks, and twists due to Earth's rotation, it generates electric currents known as the geodynamo. Those currents generate a magnetic field that extends tens of thousands of kilometers into space. This field does two critical things. It shields Earth from charged solar particles, and it gives us a reliable directional reference, or at least it used to. For most of history, the North Magnetic Pole barely moved. Then, it took off. When it was first measured in 1831, the North Magnetic Pole sat in northern Canada. For decades, it drifted slowly, about 10 kilometers per year. Then, in the late 1990s, something changed. Today, it's racing towards Siberia at up to 50 kilometers per year.
You got magnetic declination, which is the difference between true north and magnetic north, where you are in the world, has always varied, and it's generally quite slow until about the 1990s. And then at that point, the North Magnetic Pole started to move a lot faster. So it's typically kind of moving around 10 kilometers per year in northern Canada. And then around the 1990s, it started to move much faster. And it just sort of took a sort of beeline rather than kind of like moving around in a circle. It took a beeline towards the North Pole itself and then kind of past the North Pole around 2017 and went across towards Siberia. And for about 15, 20 years, it was doing maybe 40, 50 kilometers per year in terms of the rate of change it's moving. And if you think about that, that's about 1 kilometer a week, which is very fast if you think about a kind of global process to do with the polar regions. And then 10 years ago, 5 years ago, it started slowing down. So it's now moved sort of slowly back from sort of 50 kilometers a year to maybe 30, 35 kilometers a year. And on that trend, it looks like it's slowing down. In comparison, the southern pole, which kind of is offshore of Antarctica, that is moving about 5, 10 kilometers per year. So that actually hasn't moved particularly far in the last 20 or 30 years, not compared to the North Magnetic Pole.
Why is this happening? The main theory is that there's a tug-of-war deep inside the core. Imagine two huge, competing flows of molten metal in the core. Recent studies suggest the fast-moving jet under Canada has weakened, while the flow under Siberia has grown stronger. This is shifting the magnetic focus across the planet.
The whole system in the outer core is in constant motion, and it's actually quite fluidic or very low viscosity. So it's something like fluid as your liquid water is on the surface, and that makes it flow really easily. And because of that, you get different flow regimes in the outer core. And it looks like in the northern polar region, that area has been sort of caught in what we call a jet, and it's just kind of very localized region where the flow there has just speeded up in the last 20 or 30 years. Effectively, the magnetic field in that region has reconfigured itself quite rapidly compared to the rest of the world.
In other words, the compass needle isn't broken. The planet itself is changing. So where does climate change fit into this? The short answer is not as the main driver. Core dynamics dominate, but mass redistribution, the melting of polar ice sheets, for example, can slightly alter Earth's rotation and field geometry. Climate change doesn't drive the geodynamo, but it may subtly influence how Earth's mass is distributed, nudging a system that's already in motion. For engineers, the movement of the magnetic pole isn't just an academic curiosity, it's a practical problem. Magnetic north and true north are not the same thing. The difference between them is called magnetic declination, and it varies depending on where you are on Earth. Navigation systems, both old and new, must account for this difference. For centuries, mariners used magnetic compasses and corrected for declination using charts. Today, the process is digital, but the principle is the same. Modern navigation systems rely on a mathematical representation of Earth's magnetic field called the World Magnetic Model, or WMM. This model is jointly maintained by the British Geological Survey and NOAA in the United States. It's embedded in aircraft navigation systems, ship navigation software, smartphone compasses, military guidance systems, offshore drilling operations. The model predicts how the magnetic field will change over time. Normally, it's updated every 5 years, but in 2019, the North Magnetic Pole was moving so fast that scientists had to issue an early update because errors were accumulating faster than expected.
In 2015, we released the model and we had effectively underestimated the rate at which the North Pole was moving by about 5 kilometers per year. And that had accumulated over the course of 4 years to be large enough that we were in danger of moving outside the accuracy requirements for the model. We made the decision in 2018 to revise the model and release it in order to kind of maintain accuracy. We were slightly caught out by that because the acceleration went up rather than down. In the last couple of years, it's continued to go down again, the rate of acceleration, particularly at the North Pole. So we're been better able to capture that change in the last couple of releases. So I think we're confident that it's going to remain within the required accuracy for the next few years.
If the model isn't updated, navigation errors slowly creep in. Aircraft headings drift. Runway numbers no longer align perfectly with magnetic bearings. Ships and drilling platforms lose precision. And here's the key engineering takeaway: magnetism is often the backup system. When GPS fails due to interference, jamming, or space weather, magnetic navigation is what many systems fall back on. If that reference is off, redundancy disappears. The faster the magnetic field changes, the more aggressively engineers must monitor and update their models. Humans use satellites to navigate, animals use the planet itself. A wide range of species can detect Earth's magnetic field, including birds, sea turtles, salmon, sharks, bees, and even certain bacteria. This ability is known as magnetoreception, and it's one of the most remarkable sensory systems in nature. Animals don't just sense north. Many can detect the angle of magnetic field lines, the inclination, and the strength of the field, the intensity. Together, these properties form a magnetic map, one that varies predictably across the planet.
The sea turtles, which we've studied most extensively, have a remarkable array of abilities to navigate using the Earth's magnetic field. They have a magnetic compass sense, meaning that they can use the magnetic field to distinguish between, for example, north and south, much as the way we can do with one of our handheld compasses. In addition to that, the turtles can also derive positional information from the Earth's magnetic field. In other words, in essence, they can use the magnetic field as a kind of map or as a kind of GPS system for figuring out where they are in the ocean.
So what happens when the magnetic field shifts? The reassuring answer is, most animals are adaptable. The movement of the magnetic pole happens over decades, not days. Animals recalibrate their internal maps using multiple cues, including the sun, stars, polarized lights, smells, and landmarks. Research suggests that gradual magnetic drift does not significantly disrupt migration patterns. However, short-term disturbances, such as geomagnetic storms caused by solar activity, can affect animal behavior.
We've actually done some studies looking at how the changes in the local magnetic fields along the coast of East Florida, which is one of the hotspots for sea turtle nesting, how those small changes in magnetic field affect where the turtles come in to nest. And there is, in fact, a relationship between the change in magnetic field and where the turtles decide to go ashore to nest. So it does appear that the turtles are using the magnetic field to return to their home locations, and also that the slight changes in the magnetic field that occur do have an impact.
From an evolutionary perspective, this makes sense. Earth's magnetic field has flipped polarity hundreds of times in the past, and life survived every one of them. If the North Magnetic Pole is a story of motion, the South Atlantic Anomaly is a story of weakness. The South Atlantic Anomaly, or SAA, is a region stretching from South America to Southern Africa where Earth's magnetic field is significantly weaker than elsewhere. In this region, the inner edge of the Van Allen radiation belt dips closer to Earth, exposing satellites and spacecraft to higher levels of energetic particles. For satellites, this is a problem. Electronics exposed to high-energy radiation can experience data corruption, sensor glitches, component degradation, or even complete failure. As a result, many satellites shut down sensitive systems when passing through the anomaly.
The real technology effect that spacecraft operators are concerned about is not so much the fact that there's kind of a pothole, if you will, in the magnetic field, but that pothole or weakness in the magnetic field is kind of a perfect trap for energetic particles. Some of those particles can come directly from the sun, but on a sort of a long-term environmental basis, those particles are being energized in Earth's main magnetic field, and they can either drift or during geomagnetic storms, approach closely and become part of the outer or inner radiation belts. It turns out that the southern edge of the inner radiation belt intersects with the weak field in the South Atlantic anomaly, and essentially that becomes kind of a perfect trap for these energetic particles, and then the source of the problems for spacecraft that are regularly transiting that area, because those spacecraft and their instruments are going to feel the effects of these particles due to radiation.
The SAA exists because the magnetic field generated in the core is uneven. The same dynamics that move the magnetic poles also weaken the field in certain regions. And the anomaly is changing. It's drifting westward and it's growing. And recent data suggests it may be splitting into two separate lobes, which would complicate satellite operations even further.
We have seen changes in the South Atlantic anomaly on the order of 5 to 10%, and I may be underestimating that, but it has been accelerating, so it is very noticeable.
For engineers designing spacecraft, this isn't theoretical. It affects orbit selection, shielding requirements, mission lifetimes, and operation planning.
A lot of this comes in terms of technology in the planning for spacecraft missions and deciding whether or not you're going to add new levels of radiation hardening or some kind of advanced system that will identify, there's been a problem in this or that particular computer chip. We may go for an extended time without data. Will we have some other data backup that we can rely on? So it's a lot of mitigation efforts and thinking and planning about those, and in particular in a much more crowded space environment than we have lived in or with in the past.
What we've learned is Earth's magnetic field isn't breaking. It's behaving exactly like a system driven by turbulent molten metal should. The north magnetic pole is moving because Earth's core is changing. Navigation systems must adapt because our reference frame is shifting. Animals continue to migrate because evolution has prepared them for a dynamic planet. And the South Atlantic anomaly reminds us that even invisible forces can have real engineering consequences. The deeper lesson is that Earth is not a static platform, it's an active machine. And understanding that machine from core to orbit is no longer optional.